Voltage and electric current. Moving two positive charges together requires us to apply a force because they really want to repel each other. So we've got the two charges plus Q. We're going to apply a force to this one. This results in work being done on the system of two charges, since a force is applied over a distance. This work increases the electric potential energy of the system. Just like applying a force to raise an object above the floor adds potential energy to that system, and that was called gravitational potential energy. A measure of the amount of increased potential energy per charge, per unit charge, is voltage. A 1.5 volt battery, like a AA or a AAA battery, adds 1.5 joules of energy to every coulomb of charge that passes through it. Batteries convert chemical potential energy into electric potential energy. Both of these batteries have the exact same voltage, 1.5 volts. So each electron that leaves the battery has the same energy. The larger battery, the AA, has more chemicals, so it lasts longer than a AAA battery. Electrical energy imparted by the battery is carried by moving charges and used by various circuit elements such as light bulbs. A light bulb converts the electrical energy into heat and light energy, decreasing the energy of the charges and the voltage. Electric current is the rate of flow of electric charge. The letter I is the symbol for current. And here we have charge over time. Q is the amount of charge, and T is the time it takes to flow past a location. Current has units of amperes, which is more frequently called amps. Since charge is measured in coulombs and time is measured in seconds, 1 amp equals 1 coulomb per second. Analogies are used to explain electricity because you really don't see electricity most of the time. So a good analogy to help understand electric current is to consider water flow. The flow of water in a pipe is similar to the flow of electrons in a wire. Water flow depends on the pressure exerted on it by a pump or gravity. Electric current depends on the pressure, right, that's the analogous word there, exerted by the voltage. An electric circuit is an external path that charges can flow between the two battery terminals. So here's a battery here. We have the positive terminal and the negative terminal. Our external path is a wire, copper wire normally. Here's a light bulb. For charge to flow, the path must be unbroken. The wire can't be broken. It has to be continuous from the positive to the negative terminal of the battery. Frequently, we use copper wire. Continuing the water analogy, one can think of the wire as a pipe for charge to move through. A battery pushes current through a circuit like a pump pushes water through a pipe. So that's probably it for the analogies now. Charges do not move through the circuit unless there is an applied voltage. No voltage, you have no movement of charge. Batteries have a potential difference between their terminals, and by definition, conventional current moves from the positive terminal to the negative terminal. Conventional current, that's what it's called by electrical engineers. Actually, electrons, which have a negative charge, are moving in the opposite direction of the conventional current, but the effect is the same. That convention was established before the discovery of the electron, and we've just kind of kept it. All materials resist the flow of electric current to a greater or lesser extent. That is called electrical resistance, capital R. Resistance is measured in ohms. Its symbol is the Greek letter omega. Increasing resistance decreases current. Increasing resistance, current goes down. Increasing voltage increases current. Combining these relationships yields Ohm's law. Current is voltage over resistance. The units for current, of course, are amps, which can be seen to be volts per ohm by substituting into Ohm's law. Right? So for voltage, we have volts. For resistance, we have ohms. So an amp is a volt per ohm. Ohm's law can be manipulated to be in slightly different formats. So if you have voltage and current, you can find resistance is equal to V over I. Or you can find the voltage given the current through a resistance, and V is equal to IR. So it's the same equation, just with the variables moved around. When making circuit diagrams, and we've already shown you one, we use standard symbols to represent each component. This is a resistor, and here's what a resistor really looks like. Well, one type of resistor. A battery, one long vertical line, one short, and the longer line represents the positive terminal. The shorter vertical line is a negative terminal. Wires we just represent with a line. The circuit diagrams do not show where each part is physically located. Let's work an example. Draw a simple circuit that has a 9-volt battery with a 3 ohm resistor across its terminals. What is the magnitude and direction of the current? So try it and go on to the next slide for the answer. So here we go. We'll start with the battery, label it V equals 9 volts. We connect it up with a copper wire to a resistor of 3 ohms, and then we have to come back. So we have a complete unbroken path. We also could have drawn it like this, or like this, okay? But the rectangle looks a lot simpler. And again, that doesn't show you physically where they're located in your circuit. Notice we have the current over here flowing. Well, hang on, let me just go ahead and erase some of this, make it a little neater. We've drawn the conventional current coming out of the battery from the positive terminal, and we could have drawn it anywhere in the circuit because that's how it flows, but it points away from the positive terminal. We use Ohm's law. Current is voltage over resistance. 9 volts over 3 ohms is 3 amps. There are 2 ways to add a second resistor to the circuit, or then a third, fourth, fifth, etc. One is the series circuit. In that case, all charges, okay, we have our conventional current flowing that way, and just to remind you, the electrons are actually going in the opposite direction, but don't worry about that. All charges must move through both resistors to get to the other terminal. When multiple resistors are added in series, the net resistance of a circuit increases. The resistance increases when you have resistors in series. Then you have them in parallel. This is where you have charges. They'll either pass through R2 or R1, but not both. And then they'll all combine on the other side and keep flowing. When multiple resistors are added in parallel, the net resistance of a circuit decreases.